In this lecture and the subsequent lecture, we are going to talk about basics of noise and noise monitoring in machines. Well, you realize that if a machine has a fault, it would make some abnormal noise, and actually the operator or the worker is drawn towards the machine because of this noise. Something breaking, something dropping, something hitting against each other, tic-tac, loud booms, whistles, bangs. So these are some of the noise which draw our attraction to this machine, which has a concern. Of course, people do not use noise per se as a monitoring tool, because of the fact is, it becomes very difficult to separate the noise which one hears from a machine it is coming, or from a group of machines it is coming. In other words, in a noisy environment, if there are 2-3 machines making noise, it becomes difficult for anybody to really quickly understand where this noise is coming from. So noise contamination, and we will see the reason why this contamination occurs because of the scales which we use and the levels which we use. So we will see what this is. Okay. So with this, I want to talk about certain basics of noise. Now, what is this noise, or a related field of science is what is known as acoustics. Acoustics is actually a branch of engineering which deals with the generation, transmission, and reception of sound. Okay. And as opposed to, it is told as, or it is known as noise, is undesirable sound. Okay. So we have sound control engineers, we have noise control engineers. So noise control engineers, as you can see, any machinery which is making noise, so noise which is not acceptable by us has to be reduced, and that is what the mechanical engineers, survey engineers do as noise control engineers. As opposed to, you must have heard, there are sound engineers. Sound engineers are engineers which help in the sound reinforcement. For example, in an auditorium or in a recording studio, we have sound reinforcement systems both for recording and for reproduction. So these are known as sound engineers. So we must make a difference between sound engineers and noise control engineers, or sound control engineers and noise control engineers. But today in this lecture we are going to focus on this, what is known as noise. Okay. Noise is something not desirable. Okay. We have to see what this noise is, how to control it, and perhaps why this is important for machinery condition monitoring, and what are the levels associated with, and so on. So if you think of this sound pressure, it is nothing but a small fluctuation of pressure in the ambient fluid which travels from a source to our ear at a particular wave type. Okay. So this sound energy which is being generated requires a medium. Depending on the medium and the type of the source, we will have a type of wave, and then this energy is finally going to be received, in our case, by the human ear or some recording sensor which is in a recording microphone. Now, this sound pressure which we are talking about is nothing but with time. For example, right now in this room the ambient pressure is 1.0133 into 10 to the power 5 pascals, which is nothing but the atmospheric pressure here. Okay. So, P total at any point in this room is P atmosphere plus the small acoustic pressure. This is the acoustic pressure which we are going to deal about. You will see this P total is actually sensed by the human ear, which is incident, this energy is incident on the human eardrum, and even a very small fluctuation in this pressure, small pressure P, is loud enough to give us a sensation of hearing. Okay. So, if P atmosphere is 1.0133 into 10 to the power 5 pascals, on top of it a small pressure, even 1 pascal, is very loud for human ears. Okay. So, that is what we have to see. So, if you see here, this is the small fluctuation in pressure which is being incident. Now, if I talk about values, you see, depending on the altitude from the sea level, there will be a pressure variations. So, that is the atmospheric pressure, but on an average it is this small perturbations which happens because somebody is speaking, the voice signals will go, somebody is clapping. So, it is this small fluctuations or the perturbations, this is the acoustic pressure which one is interested in when we talk about sound waves. Now, these waves, this energy will go in terms of longitudinal waves, or transverse waves, or bending waves. We will not discuss much about these in this class, but you will all recall your high school physics that if a surface is vibrating here some velocity, so what happens to the air molecules immediately next to it will have this energy transferred, and it will also oscillate about its mean position, and then it will again pass on the energy to the subsequent molecules. Okay. And then we will have alternate compressions and rarefications, and this is how the longitudinal waves travel, and the distance between each successive compressions or rarefactions is the wavelength, and these molecules themselves, or the particles as they call themselves, will not move, okay, but they will oscillate about their mean position with a particle velocity, and thus transfer this energy. But this wave front is moving at a speed which is on the wave propagation speed, and for longitudinal waves in air, in fluids which could be air, water. Okay. This is nothing known as the otherwise speed of sound in air. So, there are two speeds we are talking about. One is this speed, is the speed at which this energy is going and that is the wavefront speed, but other is the particle velocity, where the velocity, the displacement of this particle or the velocity about the particle about its equilibrium position, its mean position. So, these oscillations of the particles are responsible for the transfer of energy from one particle to another and so on, and this propagation speed moves, and this depends, propagation speed depends depends on the bulk modulus of the fluid, okay, depends on the temperature, depends on the density and so on and so forth. Okay. Now, for air, the speed is 343 meters per second at STP conditions. This should vary with the temperature and so on. But then if you that was sound particle P, and where I had told sound pressure P, where I had told that the pressure is only moving in one direction predominantly, and that is a longitudinal one dimensional wave, as opposed to, imagine if I have a point source P, okay, of some power, this energy is going to radiate in all directions around the sphere. Okay. If capital P is the sound power, we have a term called intensity, is nothing but the sound power P by the area 4 pi r square, where this is the radius r. Okay. And this will boil down to P square by rho c. Okay. And I will not go into derivations of this. So, the intensity can be calculated by knowing the sound pressure. Rho is the density of the medium, c is the speed of sound, and rho c is known as the z, small z, is the specific acoustic impedance of the medium. As you will see, rho and c are the properties of the medium, specific acoustic impedance of the medium. Okay. Now, this is what I meant by the propagation of sound as a longitudinal wave. So, there are compressions, and with time there are extensions, or which are known as rarefactions. So, the entire time period of the signal or of the wave is nothing but, if I show it as a transverse wave, with time, this is the time period. Okay, and the frequency of this wave is nothing but one by time period, some amplitude x t. Okay, this is the 0 to peak amplitudes. Just to recall these things we had discussed in our signal processing class, okay, which is universally true. And because this is just a one frequency in acoustics or in sound, this is known as a pure tone. Pure tone is a wave of a single frequency. Okay. Like a 10 hertz sine wave, that is a pure tone of sine wave, okay, 10 hertz. Now, this acoustic pressure which we just described or talked about, which human ear hears, this can be a very, very low level, maybe the lowest is 20 micropascals. Okay, human ears lowest level of perception, okay, to a very high value of maybe 100 pascals. So, this is 20 into 10⁻⁶ pascals, and this highest level, higher level, or I can make it 200 pascals also, just for the sake of argument here. Highest level. Okay. So, you can see the dynamic range, which is nothing but 10 log 10 of P max by P min. You will see 10 log 10 of 2 into 10 to the power 2 by 2 into 10 to the power -6. So, this becomes 10 log 10 of 10 to the power 8. Yeah, this is 20, sorry. So, this becomes about 160 decibel. So, human ear, God has made our ears. The dynamic range is very, very large. Okay. We can hear from the faintest sound of 20 into 10 to the power -6 pascals to as high as 200 pascals. I will not, though, kind of warn you at levels higher than 100 pascals, we get a sensation of pain and there will be instant hearing damage. Okay. Having said that, it becomes difficult for anybody to handle such a large range of numbers from 10 to the power -6 to 10 to the power 2 in a linear scale. Okay. And that is the only reason we use what is known as a logarithmic scale to represent a large range of quantities. Okay. So, for sound pressure, P, which is PRMS, the levels are actually represented by what is known as SPL, sound pressure level, is given as 20 logarithm to the base 10 of P RMS by P reference, where the international standard is P reference is 20 micropascals. Okay. Now, you can work out that if P RMS is equal to 1 pascal, SPL will corresponds to 94 decibel. By the way, the SPL then is given in a value decibel. Okay. So, it is written as small d capital B, which is nothing but decibel. Okay. The convention is to write as small d and b. So, 1 pascal RMS value corresponds to an SPL of 94 decibels. So, you can see here in the slide, for the linear scale, we have the corresponding values here in green in decibel scale, the sound pressure level. They are the same thing, only thing is that we are conveying linear values in a manageable small values of scale from 0 to 140 decibels. I am in fact representing the entire range of sound pressure values which a human ear can be subjected to. Now, you will see here that some rules of logarithmic addition can be used. For example, suppose I have 94 decibel as one SPL1, I have SPL2 as 94 decibel. Okay. So, I am adding two coherent sources. This will boil down to about 100 decibel, because logarithm of 2 to the base 10 is 0.3010, and these values we are going to see later on how much it will increase, decrease and so on. So, this is the example which I was just giving you. Okay. If 1 Pascal, then the boil down to 94 decibels, whereas P is equal to 31.7, it is only 124 decibels. So, when you add decibel scales, please do not make this mistake, because log of m plus log of n is not equal to log of m plus n. This is not equal. Okay. So, never do this. So, always do the additions and subtractions in the linear units and then convert your final answer to the decibel scale. But something I must tell you about the perception of sound amongst human beings. See, if one machine makes 90 decibel and another makes 87 or 93, to our human ears we will notice no difference. Our human ears cannot perceive any difference less than 3 decibels. So, this is why one has to be careful to bring about subsequent reduction in the noise or increase in the noise. It has to be 5 or 10 dB higher. Okay. And this I will take a cue, remember this, and when you talk about noise monitoring, you will see the influence of this 10 dB and so on. Now, if you will see here, there could be different types of sound sources in our real life. One is a plane wave source. The sound pressure in one dimensions at any distance r, it is the same, the SPL becomes the same. And if I have a cylindrical source like a highway noise, this sound pressure level at any distance r, which is twice the original distance, will only decrease by 3 decibels. Whereas, if I have a point source, the sound pressure level will actually decrease by 6 decibels. Okay. And when I am talking about a point source, the pressure is actually proportional to A by R. So, inversely proportional to the distance from the source R. So, if P1 is equal to some constant A by R and P2 is equal to some constant A by 2R, you will see SPL 1 minus SPL 2 will be nothing but 20 log 10 to the base of 2R by R. Okay. And then this will become, because logarithm of 2 to the base 10 is 0.30, so 20 times 0.3010, this will be about 6 decibels. So, with every doubling of the distance, the sound pressure level will decrease by 6 decibels. And we will see later on how such rooms are available in places where the sound gets absorbed at the boundaries. These are known as anechoic chambers, and it gets reflected. These are known as the reverberation chambers. So, sound field in the free field is actually, we have the condition where the sound pressure level will decrease by 6 decibels, and all the measurements out of machines have to be actually done in the free field, and if you go close to the boundaries, they will reverberate or they will reflect, and the sound levels may increase. So, I will talk about additions and so on in the later classes. Okay. Such chambers are used for noise control in automobiles. Okay. So, sound field in enclosure, there is a direct field, sound directly coming from the source. Far field is source acts like a point, near field source cannot be considered as a point. Okay. And obviously, pressure would increase at the walls because of the reflection. Okay. So, 3 decibels, 6 decibels and so on, right. We will talk about frequency range in this sound which we talked about. Human beings can hear anywhere from 20 hertz to 20 kilohertz, and this is the audible range. So, anything beyond this is the ultrasonics, anything less than this is the infrasonic. Of course, we will see that different machines create different kinds of noise, which we will talk about in noise monitoring and so on. They say dogs can hear beyond 20 kilohertz, bats use ultrasonic waves for their navigation and so on. Okay. And of course, there is the relationship between wavelength and frequency. As the frequency increases, the wavelength would decrease and so on. Okay. We all know this from signal processing. This is a pure tone of a lower frequency, the pure tone of a higher frequency. These are two signals because it can see in the frequency spectrum and so on, right. And we will talk about these filters in the next class and so on. More of this you can find in my book. Thank you.